Hello everyone, my name is Soumya and I am a PMRF fellow at IIT Gandhinagar. It has been 12 weeks already and we have done or covered problems on all of the topics that are required for this course on control systems. So since we have already done the problems, in case you have any doubts, you can definitely ask. Or just a second. Yes, if you have any problems, then you can definitely ask. And we are going to do some MATLAB problems today. It would start right from the very basics of MATLAB and it would continue until uh, we do a couple of problems on control systems. So we are going to cover all such concepts that will help us do that. So before we start, I think we should go through this once because uh, so before when we started this chapter, we were here with this course layout, and then we started learning right from what is control, what are dynamic systems, closed loop systems, etc. We moved to stability, we moved to how do we define the stability of the system, we were stability, first order systems, second order systems, and then controllers, where we learned how important is PID controller, and it is one of the most used controllers in everywhere in industry. And then we moved to various other methods of defining the stability of the system, which is done by route service criteria from Bode plot. Also you can say if the system is stable or not. Nyquist stability criterion also does the same thing, and all of these are just different plots in the frequency domain, the Bode plot and Nyquist plot. So as we had design and as we had performance specification indicators in time domain, we do have them in frequency domain as well. And then we moved to simple controller design. We moved to frequency response, and we worked with lead lag and lag lead compensators. So that was the overview of the course. Again, I had reiterated this in the first class, in the last class, and today I'm saying this again. But the most important book for this is the first one, Biogata, Modern Control Engineering. Benjamin C. Poe is also a good book, and apart from this, Norman Nice. So all of these are good books for control engineering, and you must go through that. All right. Okay. So after this, let's start with problems on MATLAB. Uh, I see. So I don't know if you have MATLAB already installed with you or not. I'm not sure about that. So as I had communicated earlier in the last class, that for MATLAB we can have either this if your institute provides you license, or if you have purchased, you can go with MATLAB. If not, I think MATLAB provides free access to its app for 15 days, I guess 15 or 30 days, I don't remember exactly. So you can use that. Apart from this, MATLAB online is free of cost. You can always code in MATLAB online. So I do not have very good experience with Simulink in MATLAB online, but I do have a good experience with general programming that we can do. Okay. Apart from this, if you don't have access to MATLAB and you're not willing to use it because you don't have a license and you're not getting access to all the features, you can definitely go with Octave. So Octave is kind of a replacement of MATLAB, and then all the problems can be solved there as we do in MATLAB itself. So that is also not a problem. You can go with Octave. Okay. So we'll start with very basics, where we are first going to have a few questions on how do we define matrices, how do we extract something from matrix, or what we have to do if we want to manipulate the matrix. So what should we do in case we are working with two matrices. So for all of these, we are going to see some MATLAB problems and codes. After that, we'll move to MATLAB problems that will cover basically whatever you see on the screen. So I have tried to cover at least one question related to each of them. It would not be definitely an exhaustive problem solving session, but I have tried to include as many questions as possible, and all of them are very basic questions that cover that, okay, this is possible by doing this thing. So you'll get a basic introduction to all of them, that what all commands are available, what all functions are available, and what all can be used directly. In case there is no function, then how do we go about it? What is symbolic toolbox? So everything we'll see that, because that is the one which is mostly used for Laplace domain analysis. Okay, and yeah, we'll have all the questions today. So let's start. Oh, by the way, before that, uh, in case you've missed any session, all of the sessions are recorded and they are available on my YouTube channel. So as I know the exam is approaching, so you can always go through. So if you go to my channel, Soumya, you will have access to all the videos. So they are uploaded as NPTEL week 1, week 2, week 3 and so on till week 12, and today would be extra session. So feel free to watch these videos in case you have missed a session. The other thing is, if you have some problems, you can comment on the videos. I'll answer the questions there itself. So yeah, here you have access to all the videos whatever has been taught. Okay, now let's move to MATLAB. Okay, so we'll do a couple of questions today, and it would start right from the very basic concept. So if you can see here, okay, so what does, I think I will, no, I'll keep this window, okay, let it be here. So there are three statements. So when you start the MATLAB, on the left pane, what you see is the folder, all the folders that we have, etc. All of them are there. The important part is this editor where we write code. Now that code can be a live script, it can be a code broken into sections, or it can be a single script. So why do we have sections? Let's say you have a very big code and then you want to execute a section of it at a time. We break it into sections and then we run section from here. In case it is a single script, we use this run option from here and run the script. In case it is into multiple sections but you want to run all sections, then also we go for this run. And the other one is MATLAB online, which I am not touching today. So it's MATLAB inline, means you have a code and then you have output below it, then you have code, then you have output below it. So that is called live script. It's .mlx. Here we are dealing with .m file. It is just that in this file everything is broken into sections because I want to execute them. The way to define sections is have 2 percentage signs before the point you want to break the section. Okay, now on the right side what we have is the workspace. Workspace is basically when you execute a program and you have some variables defined that are being updated or that are being used in the calculation. The workspace contains the matrices, arrays, or in any other string format, whatever format it is, it stores those numbers. Okay, so workspace is basically for seeing what is the size of my output, what all values are there, what is the nature of values that is being contained here. Okay, I can save the workspace data and use it somewhere else. So this workspace is basically storing the values of all the variables that you have in the program. Next comes the command window. This command window is basically for the execution. Not for the execution, sorry, for getting the solutions to the programs. So if I, let's say, run this section, I don't have any code written over there, but if there were a code written there, the answer should be found here. This is a command window. Apart from this, you can perform very simple operations also here, like you cannot write a full-fledged code, but you can do some very simple operations, or you can use few of the functions as well. All of them can be done in the command window. But if it involves an execution in loop or too many statements that your program has to pass through, don't do it in the command window, do in the editor. Okay. Now, so for clearing the command window, the command that I'll use is CLC. It clears the command window and I get a clean command window. The other command that you see in the script is clear all. Clear all is basically, so you can see here there is a value added in the workspace because I ran it in command window. Now I want to remove it. So basically it is always replaced. As soon as you change the program, if there is the same variable, it is replaced. But mostly it is preferred that we should not have any extra variables, or there shouldn't be any garbage value. So for that we use clear all, and see if I type here clear all, that will get removed. Okay. After this we have close all. Close all is, let's say I ran some code in MATLAB, and then there were some plots generated, and let's say there were 5 plots generated. I don't need to close them one by one because that consumes my time. So I'll write close all, and everything that was running before will get terminated. Alright, so it is like task bar को use करते वक्त we use the terminate task option. So that is it. So these 3 commands at the beginning of program clears the command window, clears workspace, and it also clears if there are any plots generated or if there is any other window generated. Okay. Okay, so let's start with very basic problem that we have here. So we want to create a matrix, a 3 cross 3 matrix A with elements from 1 to 9. Okay, then we want to display, after creating the matrix, we want to display what is the first row and the last column of the matrix. That is all. Okay, so numbers are from 1 to 9. We would assume that 1 to 3 is in the first row, 4, 5, 6 is in the second row, 7, 8, 9 is in the third row. So like that will define. Now how do we define? So let's say we want to assign a matrix to A. So we'll have square brackets. Inside this, all the values for the matrices would be kept. Okay. So we'll write 1, 2, 3. This is the first row. Now we want to change the row. For changing the row, this semicolon is used. All right. Then we'll write 4, 5, 6. Again we'll break the the row and write 7, 8 and 9. All right. So in this way we define the matrix. Okay. Now after this, if you put a semicolon, it is going to terminate this line. Terminate as in it won't be printed. So by default, if there is any variable over here, it would get printed. But if you have a semicolon after this, it would not print that particular statement. Okay. So that is why I put semicolon. In case I don't put, so you can see here itself, I'll run the section, the matrix is getting printed. But if I use a semicolon, nothing is getting printed. So I'll show you once again, CLC, and now I run this section. What would happen? Nothing would get printed. So that is why this semicolon is used. Okay. Now, okay. So what do we want to do? We want to display the first row and the last column. So let's define a variable called first row. Okay. And what does it contain? It contains, we want first row. That means 1, comma, and what column do we want? We want all the columns for our first row. So for all the columns, we'll use colon. So colon means it will take all the possible values. In our case, it is 1, 2 and 3. But for the row, it is just 1. So first number is 1 and the second is colon, which denotes 1, 2 and 3, all of them. We won't have a semicolon placed over here because we want to print it. And then in the last column, what we'll have? We'll have all the rows we want, so it would be this. And then here it should be 3, right? Because we want to print last column. In case you don't have a count of the columns and you are not interested in knowing, okay, what is the size of my matrix, and then I want to print this column only, you can always write end. End means last. So it is going to fetch the value of end, and that end will be fetched as 3, and then it would print. So if you see, the first row is 1, 2, 3, and the last column is 3, 6, 9, which is printed over here. Okay, I hope this is clear. Then we'll move to matrix with ranges. So we want to create a row vector X, okay, which basically comprises of all odd numbers from 1 to 15. 1, 3, 5, etc. So why it is written like this? 1, 2 and 15, 1 and 15, and in between them there should be a gap of 2. In Python it is not this way. In Python it would be written as 1, 15 and then 2 by giving commas in between. But here it is, what is the difference that is put in between? Okay, so we want to create a row vector of odd numbers between 1 to 15, and we also want to create a column vector between 0 to 6 with a gap of 1. So essentially 6 equally spaced points in between 0 and 1. Okay, so let's do that. So let's define X as 1 to 15, right, and Y as linspace. Linspace means linear spacing. Okay, so in between 0 to 6 there should be linear spacing. Linspace 0, 1 and 6. Okay, let's print them. So we get 1, 3, 5, 7, 9, 11, 13, 15, and here we get 0, 0, 0.2, 0.4, 0.6, 0.8 and 1. Okay, so I did a mistake over here. In the linspace, it was in between 0 and 1, I want to have 6 points. I hope that is clear. And not in between 0 and 6. Okay, so we want to have linearly spaced points in between 0 and 1. Okay. If okay, let's move to the third question. It is about accessing elements. So a matrix A is given over here, which is 3, 5, 7, 2, 4, 6, 9, 1, 8. I want to extract the element in the second row, third column, and in the other case I want to extract the entire first column, and in the other case I want to extract a submatrix formed by rows 1 and 3, columns 1, 2 and 3. Okay, I hope that is clear what is meant by. So it's rows 1 and 3 means the first row and the third row, and the columns 2 and 3. So basically the bottom two values at the extremes. Okay, so let's write a code for this. So let's define this matrix. So we can directly copy from here and we won't write it again. Okay, This is the matrix, we don't want to print it, so I have terminated it. Okay, after this we want to extract 2 comma 3. So, and it's going to be just an element, so I'll write element is equal to a 2 comma 3. So element should return me the element which is placed at 2 comma 3. Okay, the second is the entire first column, so I'll name it as col 1, and then it is a, and what it should be, all the rows comma the first column. Okay, after this we want to extract a submatrix, so let's define that. Submatrix is equal to A, okay, and then we want 1, 3 and 2 and 3. So what is the first? We wanted 1 and 3, and then we wanted 2 and 3. Okay, let me run this. Okay, so you can see here the element which is at 2 comma 3 is, okay, is it not visible? Just a second. Just a minute. How do we increase the font size? I think now it should be visible. I cannot increase the size of output for some reason.
It's okay, man. Hello.
Is this visible now?
Yeah, it is visible.
Okay, okay. Why don't I have the meet screen coming over here? Okay, I think something happened.
Okay, this is okay, ma'am.
Okay. If there is
This,
something, since this
uh,
mate is not visible on my screen, you can tell if there is something, then I'll come to the screen. Okay. So the submatrix is, uh, which is formed by the rows 1 and 3 and column 2 and 3. So I hope it is clear that the uh, if it is 1 and 3 and column 2 and 3, then what are we going to get? We are going to get the first number as 5, second as 7, right? Because, or yes, by 1 and 3, yeah. Okay, the columns are 2 and 3. Okay, then after this, let's move to the next question. I think I'll join from the same window I am facing this from. Okay, I'll now. Okay, still it is not coming. I cannot do anything, I think. Okay, so then we want addition and subtraction of two matrices, A and B. Okay, so how do we do that? So let me define just a very simple 2 cross 2 matrix. Let's say A is equal to 1, 2, and when I change the column, it's 3 and 4. Okay, I want to terminate it. Then I define another matrix, which is B, and it is 5, 6, and then it is 7, 8. Okay, I just have to find the sum and difference. So if I do sum AB, it's going to be just A plus C. And if I want to find the difference of AB, it's going to be, so there is a function called display function. If you write disp and inside that you write what you want to print, it prints that way. Here if we don't put a semicolon, it would just print. Okay, so diff is equal to A minus B. Okay, if I run this section, it would be the following. So summation and difference. Okay, so it is just very simple, A plus B, A minus B. This is how the matrices are defined. Okay, after this, let's move to scalar operations. So multiply the first matrix A by 3 and add 5 to every element. Okay, so let's define the same A matrix. Okay, now after this, what do we want? We want first multiplication. Multiplied is equal to 3 into A. So in this way you get 3A. First thing is this, every element of A is multiplied by 3. Now what do we want to do? We want to add 5 to every element. Right. So if I write added is equal to multiplied plus 5. Okay, so this is what I want to print. I'll run the section and I get this. See, if we want to multiply by a scalar to every element of the matrix, it just have to be a multiplication sign. Okay, but what if we want to do matrix multiplication? Okay, so how is this both differentiated by MATLAB? So let's say I define the same matrix. Okay, after this, if I want to do element wise means 1 into 5, 2 into 6, 3 into 7 and 4 into 8. That would be the answer. If you want to do matrix product, which is A into B, matrix ka rule laga ke, row into column and all that. So both doing both are different. The ways of doing both are different. If you want to do element wise, it's going to be A so dot into B. So this is called element wise. Okay. If you want to do matrix product, it's just going to be A into B. So both of these are different. The first one is element wise, in which 1 into 5 is 5, 6 into 2 is 12. Okay, 7 into 3 is 21, 8 4 is 32, and matrix multiplication is different. Okay. Okay, let's move to transpose and determinant. So find the transpose and determinant of matrix A. So I'll define a new matrix here because I want to go for 3 cross 3. Let the matrix be 2 4 1 0 3 5 and then 7 1 2. Okay, let's say this is your matrix. You don't want to print it. For getting the transpose of A, what is it? It is A transpose. Okay, for getting the determinant of A, it is det A. Okay, we run this section, we'll get the determinant to be 121 and the A transpose to be transpose of the matrix 207 etc. Okay, it's that simple. So it is in this way we find a transpose, in this way we find a determinant. Okay, if you want to find what is the inverse and rank of the matrix, what do we do? So let's define a matrix. Four, 2, 3, 1. Let's say this is our matrix, and then we want to find the inverse. How do we write it? We write INV A. Okay, and then if you want to find the rank of the matrix, just rank of A. Okay, let's run this. So you get the rank to be 2 because there are two independent, linearly independent rows and columns, and A inverse of A, which is found here. Okay. Okay, let's move to the next question. How do we define identity ones and zero matrices? So instead of defining identity by writing 1 0 0 0 1 0 and 0 0 1, how can we directly define it without defining the matrix? These are standard matrices, right? We don't need to always define it by saying, okay, this is my identity matrix. So it should be done by some function, right? So I is equal to E by E. This is for identity matrix. You write E by E and then you give what is the order of that identity matrix it would do. Okay. If we want to define ones matrix, so it would be by, let's say, of 3 comma 2 dimension, 3 rows and 2 columns. It would be 3 comma 2. Okay. If we want to define zeros matrix, so it's going to be zeros matrix is equal to zeros, let's say 2 comma 3 dimension. So you can see here, this is the identity matrix of 4 dimension, this is ones, and here it is zeros matrix. Okay. After this, finding eigenvalues and eigenvectors. So what do? We'll just find, okay, so let's say your A matrix is let's say 2 0 and the next is 0 3. Okay, terminated. Then we want to find out eigenvalues and vectors. So it is going to be just, let's say we define it as V and D because there are two things, eigenvalues and eigenvectors, equal to EIG, sorry, EIG of A. What happened? Sorry. Okay, so you get the vector and the after this we want to solve some linear equation. So for example, you have to solve this. You want to find the values of x and y here. Okay, so 2x plus 3y is equal to 8 and 5x plus y is equal to 9. Then how can we solve it? So what we can do here is we can define an A matrix which comprises of 2, 3, 5 and 1, and then B matrix we can get from 8 and 9, and then we have to find the inverse of A and multiply it with B to get the values of x and y. So you know Ax is, I think I have current tab, I'll see if it is connected. I have lost the connection, just a second. Okay, so if I have a linear equation of the form Ax is equal to B, how do we find x? We find x by A inverse B. So here in this x comprises of x and y. Okay, and this A matrix and B matrix is what we have on the right hand side. A matrix is what we have on the left hand side. Alright, this is what we are going to do. So, okay. So how are we going to define? So we are going to define a matrix as here it is 2, 3 and 5 and 1. So 2, 3, 5 and 1. Okay. What is the B matrix? B matrix is 8 semicolon 9, right? What do we want? We want to find the value of x, and what it is? It is A inverse B. The other way of defining the inverse is in this way: A and this oblique sign and then B. This B should have been small because that is how we usually write. So it is B. And this is the value of your x. Okay, so the first value is x, the second value is y. 1.4615 and 1.6923. Okay, let's move to the next question. 12th question. Element wise logical indexing. Replace all the elements greater than 5 with 0. So let's say we define a matrix with some random values. So let it be 2, 5, 7, 1, 8, 3 and then 9, 4 and 6. Okay, let's say this is our matrix. Okay, now what we want to do, we want to replace all the elements that are greater than 5 with 0. So what we'll do, we will replace in A matrix only. So we'll name that matrix to be A. Now what is that matrix? It is going to have all the values of A matrix which are greater than 5 to be equal to 0. Okay, so let's check. See, you don't see any value greater than 5. All of them are replaced by 0 now. Okay. Okay, let's move to the next question. Row and column operations. So we want to swap the first and the last rows and multiply the second column by 2. Okay, that is our goal. So let's define a matrix. Let it be very simple this time. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So what we want to do, we want to swap the first and last rows, means row 1 and row 3. So A is what is the row number? 1 and 3, right? And what are the columns? All the columns are to be replaced by A which one? 3 and 1. And what columns? All the columns. So this is for the swapping of first and last column. Okay, so in this case the matrix A is modified as the following, that the rows are swapped. Multiply the second column by 2 is the next thing that we want. So A, all the rows comma 2, which means the second column is 2 into what we had earlier. So it is basically going to be the same. It is just scaling. Okay, so let's run this section. So here you get two matrices in which the columns are swapped. 741 comes here and 963 comes here. Sorry, the rows are swapped. 1 2 3 comes here and 789 comes here. And here the second column is just multiplied by 2. So 8 5 and 2 are multiplied by 2. Okay, I hope this is clear. So this is how we swap between the columns. Okay. Okay, after this we'll do matrix concatenation. What does that mean? Let's say there are two matrices that are given to you and then you want to just concatenate it together. Okay, so how do we go about that? So let's define two matrices. It is 1, 2 and then 3 and 4. This is the first matrix. The second matrix is 5, 6 and then 7 and 8. These two matrices are there. So we want to concatenate them once horizontally and once vertically. So we can write horizontal is equal to A, B. Okay. Then vertical is equal to A, and how will write B here? By giving a semicolon, because we want to change the row. So it's going to be B here. Okay, let's run it. So here it is 1 2 3 4 and 5 6 7 8 is concatenated here. Here it is in the column. All right. Okay. Okay, let's go about this question. So we want to define a function and that should return the mean of the row or the sum of the column and the max element. Okay, so first let's define a function. How do we define a function? Function. Okay, let's say my function should take the following arguments. What are those arguments? Or not take the following arguments, they should take the argument as A only, but they should return the following. Okay, they should return row mean. Okay, then they should return column sum, and then they should return max element. Okay, this is what I want my function to return. And how, from where it should come? It should come from passing the matrix to a function named matrix stats. Okay, so it should be passed to this function. From here I can write row mean. Here I have to define what are these things. So row mean is equal to I want to just a second. So row mean is mean A, comma 2. Why 2 here? Because we want to take mean across the rows. Okay, sorry, we want to take the mean of the row across the columns. So if let me change this. Row is our first index, right? Column is our second index always. So why it is for row here, why it is 2? It is 2 here because it is mean of the row, but it is across the columns. Alright, since it is across the columns, it is 2 here. Okay, now after this, column sum is equal to sum A, matlab matrix A, comma 1, because it is summing columns but across the rows. Got it? I hope this is, so when we'll see the result, you'll be able to understand if it is not clear. And then it is max element which is max of A all the elements of A. Okay, and then we'll write end because we want to end the function. Okay, now let's call this function. How we'll call this function? Let's define a matrix A, which is given as, say, 1 2 3 4 5 6 7 8 9. Okay, so let's say this is the matrix. Then we will use the same variables here, and in this we'll pass the matrix A. Okay, so let's, sorry, so here what happens, see, row mean is why it is printed 2 times, I think I ran 2 times. Okay, so here row mean is 2 5 and 8. Check the row mean, it should be across the row. 3 plus 2 plus 1, which is 6. 6 by 3, which is 2. 6 plus 5, 11 plus 4, 15 by 3, which is 5. And 9 plus 8 plus 7 by 3, which is 8 over here. Column sum means sum across the columns. Means 1, 4 and 7. Sorry, it is column sum, right? 1, 4 and 7. Sum across the rows. Okay, so 1, 4 and 7. So it is 8 and 4, which is 12, and then 2 and 5 and 8, so it is 15, and 3 and 6 and 9, which is 18, and max element from the complete matrix, which is 9, which comes over here. Okay, I hope this is clear. So this is how we have learned something on how do we define the matrices and everything. Now let's move to the next control system part, where we will do a couple of questions on control systems. So initially when we did the very first thing we started with was introduction to Laplace transform, right? And how did we go about it? So if you want to represent a differential equation as a transfer function, how do we do it? Okay, so we just have to write what is the numerator, what is the denominator of the transfer function, and then magically it comes out to be here. So before that I'll clear this command window. Okay, so let's say so how do we define it? I say my numerator is equal to 5. Okay, and then I say my denominator is equal to, let's say 1 3 2. Okay, and then I define a system given by sys in which TF is the function in which I am passing numerator and denominator. All right, and then I'm printing it. So what it is basically, I'll show you. Okay, if so as I said, my numerator was 5, my denominator was 1 3 and 2, right? What does this represent? when you write this, the rightmost term is s to the power 0, then s to the power 1, then s to the power 2. So accordingly, this should be s to the power 0. So the transfer function that we get corresponding to this is 5 s to the power 0, which means it is just 5 upon s square plus 3s plus 2. This is the transfer function that we get when we define in this way. So TF takes in numerator and denominator and returns the transfer function in this form. Okay. So if you run this, you will see the transfer function over here. Okay. Okay. After this, if there is a differential equation given to you, let's say your differential equation is if your differential equation is, let's say, sine 3t. Okay. And we should add, because you know that Laplace transform of sine t is sine 3t, right? It would be just 9 upon omega square plus 9. It is very simple. Now I'll add somewhat complexity to it by multiplying an e to the power 80 term over here. So exponential minus 2 into t. Okay, so this is my term and I am multiplying it here. So this is my f, which is represented here, and then I want to find f, which is, so again, Laplace is a function that I am using that completes, that calculates, that changes the differential equation to Laplace form. Okay, so Laplace f. Now, how would this happen? Because it would happen only if our code knows that this t is a symbol and it does not expect any value of t. For example, if you want to define a variable and you want to get the answer in the form of variable and you don't want to put the value in that variable, how would that happen? For that, we have a symbolic toolbox. Okay, so you can define sims, which means symbolic toolbox, and then you can write here t and s. Okay, though s we are not using anywhere right now, so there's no problem, but t we are using. So what this does is it takes all the values, so it does not expect a value of t over here, rather it treats it as a variable and then tries to answer. Alright, so if I run this section, see your f, so since I did not put a semicolon over here, this also got printed. So your f is 3 upon, how is this coming? So if there were no exponential term over here, it would have been 3 upon s square plus 9. Since minus 2 came over here, it is reflected here as s plus 2. So this is a basic Laplace rule, that if you have an exponential term multiplied over there, it would appear here with us. Okay, so that is why it is here. Okay, let's move to the next question. So here we have something on transfer functions, poles and zeros. So let's know how can we get the poles and zeros directly from the transfer function. So let's say I have a numerator, which I would just keep it very simple as 10. Okay, then I have a denominator, which is, let's say, 1, 6, 11, 6. Okay, so this is the denominator, and then I want to find out the transfer function, because if I have a transfer function, then only I'll be able to calculate what are the poles and zeros. So sys is equal to TF of numerator comma denominator. Okay, this is done. After this, so this is I'll print this. So after this, what we'll do? Okay, before this, let's print it first. What happened? Acha, TF. Okay, so this is a transfer function. Now, after this, what we'll do? We want to find the poles of this transfer function. So poles is equal to pole. Pole is again a function, okay, which takes in the transfer function of the system and returns the poles. Then similarly, there are zeros, and again we have a function called zero, which takes in the system and we get zeros. Okay, so from here, let's run this. So these are the poles. Sorry. So these are the poles and zero of the system. You see there is no s in the numerator and hence we do not have any zero over there. But we have 3 poles. Alright. And by the way, you should see this. I think you are missing on this. Since I have not cleared the workspace anytime, all of the things that we have done till now are present over here. A matrix is being replaced every time because I am changing it every time, but the rest other things are here. I have not cleared the workspace, and you can see, so at some places you can see the dimensions, at some places you have direct access to values. So all of these things are there. See, the determinant is here 121, what we did, element is 6. Okay. Okay, so once we have the zeros of the system, how do we find the step response of the system? So what do? We just do step and sys. So step and sys would give me the, because ultimately we need open loop system for finding out the step response, right? So this is the transfer function, planned transfer function, and for which we are trying to find the step response. What happened? Why didn't it come? Yeah, this is the step response. Okay, so you see it is rising from 0 and settling at some point less than 1.65 or 1.68. Okay, now we got the step response of the system, but we did not get what is the overshoot, what is the peak time, what is the settling time, what is the rise time, etc. So for that we have another command which is called step info of the system. Okay, once you run this, then you get the plot, and here you can see rise time is 2.7 seconds, transient time, settling minimum time, settling maximum time, overshoot, undershoot, peak, and peak time. So this peak is peak maximum overshoot. Okay, so we get all these values. All right. Okay, let's move to the next question. Response and BIBO stability. So for the same system that we have defined over here, sys, okay, we will do the further questions. We want to know if the system is stable or not. It is so simple. Is stable is the complete function. Is stable, sys. Okay, if you run this, you'll get either 0 or 1. The 0, if it is 1, that means the system is stable. If it is not stable, it would be 0. So when we write a transfer function and try to find out where are the poles and zeros of the system, so this was already verified. The poles of the system are -3, -2 and -1. Right, so the system had to be stable. Now that you're getting from here as well, as it is a logical value. Okay. Okay, after this we want to say we want to find impulse response to the system. So we'll just write impulse sys. Okay, and let's check it out. So this is the impulse response to the system. It settles to 0 at some later point of time, but when an impulse is given, the response moves to until 0.75 and then it settles down to 0. This is the impulse response of the system. So impulse is the function which is used over here. Let's say we want to find ramp response of the system. Now there is no keyword like ramp, as impulse sys is there, ramp sys is not useful. So we'll define the ramp on our own, and how it would be? It would be, let's take t, and t lies in between 0 to 10 at, let's say, an interval of 0.1, because I want to have many points, that is why I have taken 0.1. So this is my t, and then my ramp is equal to t, because ramp is directly proportional to time, right? It's a linear relation between them. Now you can have 2t, 3t, whatever, it is unit ramp here. Okay, and then we want to what is this? Okay, so this is for plotting the time response of dynamic system. So this is LSIM, okay, and it would take in the argument system. Then what is to what you want to do, to what input you want to do this, it is R, and with respect to time. Okay, so this should give us the ramp response as, sorry. Okay, so you can see here this gray line is the unit ramp, and the system behaves in this way to the unit ramp. It also has a ramp behavior itself, but it is not completely with a ramp. So this is the behavior observed. Okay, so LSIM is for plotting the, like, taking the transfer function and giving it an input with respect to time. Okay, let's move to the next question, which is effect of zeros and first order systems. So it would basically happen that in one case you'll have a 0, in the other case you won't have a 0. So let's take two transfer functions, one with a 0, one without a 0. Alright, so let's say I define a system 1, okay, which has a transfer function of 1, comma, let's say 1 and 3. So I'm going only with first order system 1 and 3. Okay, so this is the transfer function of system 1. Sys 2 is transfer function of, here we are going to introduce a 0, so we'll have 1 and 2, okay, and then we'll have 1 and 3. So this is our second system. In this we have a 0 over here. So we'll find the step response of each of them on the same plot, and it would be defined in this way: step of sys1, and let's say I want to have that in blue color, so I'll have B. Okay, then sys2, and then I'll have it in red color. All right, the legends for each of them would be, for the first one it would be without 0, because system 1 does not have any 0. So it would be without 0, and then for the second system it would be 0. Okay, let's plot it. Okay, so this is the response that we get. So for the first system, it just rises and settles at a value of 0.33 approx. For the second system, if you see at time is equal to 0, it would rise to a value of 1 and it would settle in the other direction. Like there is a high overshoot present over here. So this is with 0 and without 0. Okay. Okay, next let's move to the next question. So this question is about second order system. So if it is a second order system, we should have some values of omega and zeta, right? And then we should do something. So what is, let's say our omega n is 5, sorry, omega n is 5 and zeta is equal to, let's say, 0.3, because I want to take an example of underdamped system. Okay, then sys, what is my system? It would be transfer function, which has to be defined in what way? It has to be defined as omega n square, and what is the second, what is in the denominator? It is s square plus 2 into zeta into omega n, right, and omega n square. So I have defined my system in this way. Okay, so I want to find out, let's say, step response of the system. I also want to find out step info, which would give me everything, the overshoot and everything. So step response of system. Okay, so let's run this. So you can see, since it is an underdamped system, we have peak overshoot and then it settles. So you can see rise time is 0.2647, transient time and settling time is 2.24, overshoot is 37. Just a second, where is this product? Yes, 37 means overshoot is of 37%. So after 1, it has almost risen to 1.38 or something, and then it settles. I hope this is clear. Okay, so this is an example of underdamped system, and this is how we have done once we knew the value of omega n and zeta over here. Okay. Okay, let's move to the next question, which is about PID controllers. So let's say my plant is given by transfer function which has 1 in the numerator, okay, and in the denominator it has s square plus 3s plus 2. Okay, so this is my transfer function, and then I define my controller by C, which is PID. PID is a function which basically takes in the values of Ki, Kp, Kp, Ki and Kd in sequence. Okay, so my controller is PID, which takes as Kp as 2, okay, Ki as 1 and Kd as 0.5. Okay, so I want to find out what is my closed loop transfer function. So closed loop transfer function is given by, so there is again a function which I am introducing here, is feedback. Okay, so this feedback, what does it do? In feedback we should have open loop transfer function, and then what is the feedback? Okay, so the open loop transfer function here is given by C into plant, right? C into plant. And what is the feedback? Feedback in this case I assume it to be unity feedback, so I'll take it as 1. Okay, and then I'll write step response of system closed loop. Okay, so this is with a PID controller. Okay, I think this is clear. So feedback, what we learned here is there is a PID function and there is a feedback function. These things are important. Okay, let's move to root locus. So let's say the numerator is given by 1, same as the earlier case, and denominator is given by 1, 3, 2. I'm taking the same case as earlier. Okay, after this my system is transfer function of numerator comma denominator. Okay, so this is my transfer function. Now I want to find the root locus for this. So the command is r locus of system. All right, so just run it. So this is the root locus. If you can see here, this is the 0 line for the real axis and imaginary axis. So the complete root locus lies in the left half of the S-plane to this 0. That means the movement of poles as the system parameter is varied is going to stay always in the left half of the S-plane. So the system is stable. Okay, for all values of k. Now let's take one value of k, which is 10. So this is what you learn from root locus, and the command is very simple, which is r locus. Okay, let's take a value of k, which is 10. Okay, what will we do after this? We'll write system closed loop feedback. I'll define the feedback because I want to take the step. I want to find the poles of the closed loop system. So it would be feedback k, because k is the gain, into system, and let's say feedback is 1. Then I want to find what is the pole of this closed loop system. Okay, let's check it out. So the poles are here, minus 1.5 plus 3j, minus 1.5 minus 3j. So both of them lie in the left half of the S-plane. So we checked, just for a check we did for k is equal to 10. We can check various values of k. But we saw from the root locus itself that it lies always in the left half of the S-plane. So for any value of k, the closed loop poles are going to lie in the left half of the S-plane. The system is going to be stable. Right. Okay. Let's move to the next question, which is about frequency response and Bode plots. So again, let's define a transfer function. Okay, which is given by, let's say our numerator is 10. Okay, and our denominator is 1, 2 and 10. Okay, so for finding and drawing the Bode plot, we just have to use the function called Bode sys. Okay, and for finding out the margins, what you can do, you can write margin sys. Oh, sorry. All right, so if we run this, so we did not get anything in the command window, we just got a Bode plot here with gain margin as infinity and phase margin as 53.1 degree at 4 radian per second. Okay, so the gain crossover frequency is 4 radian per second and the gain margin is infinity here. Okay. So you can see 53.1 degree from here, this thing, this point basically. The phase is minus 126 degree. If you subtract it from 180, you will get it to be 53.1. Okay, and where it crosses the where the phase plot crosses the minus 180 degree line, it is never happening, so gain margin is infinity over here. Okay, so the thing was very simple function called Bode actually gives us the Bode plot of the system. All right, after this if so here we'll see all the margins, so let's go into this. So if you want to find out the Nyquist plot of the same system, it is just going to be Nyquist, and here we are going to have system. Okay, so this will give the Nyquist plot, and here we can find out what is the gain margin, phase margin, gain crossover frequency, and phase crossover frequency. Okay, sorry, is equal to how are we going to get this? Using margin sys. All right, so let's check this. So this is the Nyquist plot, and if you can see that here is the minus 1 comma 0 point which is not being intersected by the Nyquist plot. Okay, so the system is not unstable as of now. Okay, after this what you can see in the command window, gain margin is infinite, phase margin is 53.1301, gain crossover frequency is infinity, and phase crossover frequency is 4 radian per second. Okay, this is what you get when you use margin function, and Nyquist system gives you the Nyquist plot. All right, now let's move to the next question. So this, okay, so this is about Nyquist stability criterion check. So this is just plotting the Nyquist plot only, it does not have anything different. It is just going to be plotting the in the similar way. This is, so we just have to change the definition of system over here. Your system is going to be defined by this. All right, and then you can just write Nyquist system. That is all here. So I won't be doing this because it is very similar to the one which we did here. It's just defining the system. Okay. Let's move to the next question, which is about lead lag and lead lag compensator. Again, we won't be designing any compensators over here because that is a long process and you can try it on your own. But let's say if I am given the transfer function of, if I have arrived at a transfer function of lead compensator or lag compensator, then how are we going to change or check if the system is unstable or unstable? So it is going to be again through the step response. So I'll solve this question by giving a sample compensator. So let's say our transfer function is in the numerator it is 1, and in the denominator it is 1, 6 and 8. Okay, then if I have a lead compensator which has the transfer function of 1, 3, okay, and 1 comma 10. If let's say this is my lead compensator transfer function, then how can I define my system lead or the closed loop function of the plant or of the system? Sys lead is equal to feedback. Okay, feedback function we already saw, right? So it would have G into D lead comma 1. All right, and then we can find the step response of the system. The step response would be step sys lead. Okay, so okay, so we see that the system has stabilized at the steady state value. Okay. Let's move to the next question. State space representation. Okay, so this is the transfer function and then we want to convert it to the state space. So let's define the numerator. It's 10. Okay, and then denominator as 1, 3 and 5. Then the system transfer function is system transfer function is TF numerator comma denominator, right? This is the system transfer function, so I'll not close it. So A can be defined as A can be defined as system SS. So no, I did some mistake over here. I'm sorry. System transfer function is given by this, and then I want it to be there in state space form. So it would be system state space, and it is given by SS, system transfer function. Okay, so this is how I went to state space representation. Now I want to extract the value of A. Similarly, okay, this is B, this is C, this is D. Okay, this is again B, this is C, and this is D. Okay, so this is how I have defined the transform. Now let's see what are the values that we get for each of them. So from here you can get the values of A, B, C, and D. Okay, so the way we do, we get the transfer function and then we check the order of the system, we assign those number of variables, and then we try to use and then we try to split in such a form that we get the state space representation, right? So all of them are already done by MATLAB in this way. In this way you can find out A, B, C, and D matrices, all of them. Okay, let's move to the next question. So we want to find out the eigenvalues and stability from the state matrix. Okay, so we will find what are the eigenvalues first, right? So eigenvalues, okay, is equal to eig of A. All right, once we have the eigenvalues, then what we'll do, if all means all the values, all values, real part of, because we want to check the real part of the poles, right? Real part of the uh, eigenvalues are less than 0, then I want to display, okay, what do I want to display? I want to display, let's say, system, we should have this, sorry, system is stable. Okay, why? Because all eigenvalues have stable real, sorry, negative real part. Okay, after this, what I should write? There should be an else statement. Okay, then I'll copy this. Then I want to display system is unstable because some eigenvalues have positive or 0 real parts. Okay, so this is how I want to do, and then I have to add this end this if else, so I'll use end over here. Okay, so let's run this section. So this is, we already saw the eigenvalues are minus 1.5 plus 1.6 and 1 plus minus 1.6 j. They are conjugate pairs, so system is stable and all eigenvalues have negative real part. So what it basically does is it checks the poles of your system. Well, this is what MATLAB does. It checks the poles of your system and then it checks all values or real part of poles. Sorry, I'm writing it here. It checks the poles of the system and then all real part of the poles if they are less than 0. That is what MATLAB does internally when it checks the eigenvalues using EIG. Okay. This is the last question that we have for today.
Okay, ma'am.
So, do you want to say something?
I got it.
If you want to say, can you write in the chat box because I'm not able to hear anything. Oh, there is a question remaining. Okay, so let's study about this DC motor control. So if you know the transfer function, so I'm not going to derive the transfer function, but what happens in DC motor control, that the transfer function of speed upon voltage is given by K upon, where K is some torque or torque constant or EMF constant. It is given by K upon Lj. So this is armature inductance. This is armature inertia. Okay.
Ma'am, it's not visible what you are writing.
Uh, I'm not able to hear you. Please type here. Okay, what I'm writing is not visible. Okay, okay, okay. Sorry. Okay, I hope it is visible now. So this is about DC motor control, and we want to find out a transfer function in between speed and voltage. So it is K, which is torque constant or EMF constant, and here it is armature inductance and armature inertia, plus uh, LB plus RJ. Okay, so this comes from friction, and this R is armature resistance, into S plus uh, RB plus K square. So this is the transfer function that we have for motor control. So we are just going to have some random values for all of these, the values which are commonly used, and then we are going to find out what is the transfer function of the motor. Okay, and then we are going to see the step response as well. So this is the last question that we'll be doing today. So let's say the value of J is 0.01 and B is equal to 0.1. Okay, K is equal to 0.01. Okay, and then R is equal to 1 and yeah, L is equal to 0.5. Okay, so as we saw, our numerator is just K. Okay, and our denominator is L into J, or I'll keep no spaces here, but okay, plus L into B, right, plus R into J plus R into V plus K square. Alright. So then we want to find out what is the transfer function of the motor. So motor is equal to TF, and inside TF will just have numerator and denominator and will not suppress it. So the step response of the motor is what we want to find. Okay, let's run this. So this is the step response of the motor. Okay, and the transfer function that you obtain by substituting all the values is over here, and this is the step response of the motor. You see there is no overshoot, and it rises and settles at a value of 0.1. All right, so what we have essentially done today, we have not done very tough questions. The questions were pretty easy. The whole point of doing this session was get an introduction to all the functions of the MATLAB that are basic building blocks in control systems. Because when you know these functions, you'll be able to solve complex problems in control system. Also, for those who were completely unfamiliar with MATLAB, the whole point was that you get introduction to how do we define matrices, how do we play with them, what are the basics of MATLAB, and it is not rocket science, it is simple to do. So you can always do this. Apart from this, in home there is something called Simulink. If you click on this Simulink, then let's say I take a blank model over here. It's taking some time to open.
Thank you, ma'am.
I think it will take some time. So the okay, it has opened. So here you can see we have library browser over here, and when you click on this library browser, you'll get access to many of the tools that can be used as drag and drop, and then you can make a model by combining all of these. And from here, like if you want to implement a PID controller and have several transfer functions, one way is go to through the code, but the other way is to go from here. So you can see there are a couple of toolboxes here, not couple, many of them. So here is this control system toolbox. For example, let's say you can take a transfer function block from here, or you can take a second order block from here, and all of them are drag and drop. You can always, so everything that you see in the workspace can actually be seen here as a graph through scope. So this Simulink is of great use, and one should learn this in MATLAB as well. All right. So the whole point of covering this MATLAB lecture was that we should have uh, a nice overview of how things are being used in control system, and what are the basic building blocks. And yeah, since this is the last day of the lectures, I don't know if you have some doubts, then we can go on with it, or all the best for your exams. I hope you do well. Go through all the lectures that was covered by the Professor Shankaram, and also go through all the tutorial sessions that we have done, all the assignments that you have solved. All the tutorial session videos are also available, all the slides are also available over the internet. Please go through all of them, and if there is something I can take.
Yeah. Thank you, ma'am. Thank you so much.
I cannot hear, I'm sorry. Due to
Oh,
some reasons,
okay.
my speakers are working really bad. Okay. Yeah. Thank you for attending the lectures as well. So I had a very nice time teaching this course. I was teaching this course for the second time, and um, yeah, this was just a problem solving session, and I hope it is of some help to everyone who have attended. So okay, I'll take your leave. Thank you so much. Bye.